Alright, today we'll be talking about powers and roots of complex numbers. Okay, so this right here is going to be all the new definitions you'll be learning, and these two bad boys are going to be the new formulas we'll be learning as well. But before we really start, let's go ahead and take a look at an escape set, or the difference between an escape set and a prisoner set, and then a Julia set and a Mandelbrot set. And there's some really cool stuff that we'll actually work with. Okay. So points that escape to infinity under the iteration belong to an escape set of the function. Okay, so in other words, we're talking about an iteration function. Okay, so if you're doing an iteration function and you're finding that it's never decreasing, it's not going to anything, you're actually dealing with a escape set. So it's an iteration function right there. So this is an iteration function that goes to infinity. Okay, so let's go out infinity, and that's Alt 236. Okay. All right, now prisoner set is going to be something that does not escape to infinity. Okay, all right, and a Julia set is actually going to be something in between the two. Okay, so I'll show you some pictures of it just so we can see what we're talking about. Okay. So first off, the Mandelbrot and the Julia sets. So let me go ahead and show you the two. Okay, so there's Mandelbrot and a Julia set. Okay, and these are just iterations with colors being designed at certain points. Okay, and the colors were added later. Okay, so these images come from the Mandelbrot set, and the Julia set one is right here. Okay, so we take a look at it. It's a really cool thing, and if you were able to actually zoom in on any spot, you would actually see something that looks similar to what's originally outside. Okay. Alright, so let's do some actual talking about the actual definitions. Okay, complex iteration, a review of complex arithmetic. Okay, so if you wanted to actually go here, this is classes at Yale slash or comma or classes.yale.edu/fractal slash Mandel set. Okay. Alright, now the Mandelbrot set is the set of all C, and we'll call it, C is just going to be a number that you're going to be adding with Z, for which the iteration of Z goes to Z squared plus C, starting from Z equals 0, does not diverge to infinity. Okay, and Julia sets are either connected one piece or of a dust of the infinitely many points. The Mandelbrot set is those C for which the Julia set is connected. And Julia sets are for complex number C. The filled-in Julia set of C is the set of all Z in which for the iteration of Z to Z squared plus C does not diverge to infinity. And remember, the Julia set is in somewhere in between a prisoner set and an escape set. Okay. All right. Now this website is fractal.org. Okay, and the Mandelbrot set is a set of all points on a complex plane. To build the Mandelbrot set, we have to use the algorithm based on the recursive formula or the iteration formula. Z sub n is equal to Z squared sub n minus 1 plus C. So you're adding the term before. And separating the points of the complex plane into two categories: points inside the Mandelbrot set and points outside. Now the image below shows a portion of the complex plane. The points of the Mandelbrot set have been covered in black. So this is just an example of what it is. It is also possible to assign a color to the points outside the Mandelbrot set. Their colors depend on how many iterations have been required to determine that they are outside the Mandelbrot set. So as you can see, we have some pink coming off the edges. Okay, and how you just start is you start from Z equals 0 and just work that way across. So let me show you an example of what it actually looks like a little bit easier. Alright, and here's a website that actually is a dedication. Benoit Mandelbrot came to the US and he worked for IBM, and he passed away in 2014, and he actually came up with the stuff for the actual Mandelbrot set and plus fractals in whole. Okay, and here's an actual picture of him. He's a really cool guy. He was a really amazing mathematician who thought outside the lines, and he came up with a lot of ideas that actually come up with just fractals in general. So here's an actual zoom. So this is actually going to be really a sweet picture. As you can see, we're zooming in. It looks like we're zooming in on this spot right here. As you can see, as we get closer, this looks like the entire big picture we just came from. Then if you notice, that does too, but so does this. But this was naked to our eye in the very beginning. Okay, and the more we zoom in, the more we begin to see what was in the beginning. And it's just amazing how it works. Now if we pick another side to actually look at this, look at this. We're going to be zooming in on a point right here. It's a whole nother world. It's just so amazing how complex we could actually get by going in here. And all you have to do is just change a couple of colors and you get these really cool patterns. Okay. So let's start talking about this. So we've talked about the iterations and everything, and what you're doing is you're doing it repeatedly, so we want to actually do some actual formulas on it. So we're going to use de Moivre's theorem. Okay, and de Moivre's theorem is if you got r CIS theta to the nth power, you're going to raise the modulus to the nth power, and that you're going to take n and times it by the argument. Okay, so for example, if we had, let's say, 2 plus 2 root 3 I, and we raise that to the 6th power, how would we do that? Well, first we would actually convert this to polar, so r would equal the square root of 4 plus 12. Sorry, I'm giving away the answer, which would actually just turn into 4 right there. So that would be our r. Alright. Now if you're wondering how I got that 2 root 3 squared is going to be 4 times 3, which is 12. Okay, and then theta is going to be arctan of 2 root 3 divided by 3, which is definitely going to turn into pi thirds. Okay, so we have that all set up. So this technically actually becomes 4 CIS pi thirds, and you're going to raise that to the 6th power. So this is now in polar form. Okay. All right. So now that we got, and the reason why this all came about was because back in the day they didn't have calculators that could do these calculations, so they had to come up with different methods, and one was converting to polar complex. Okay, so this becomes 4 to the 6, okay, and then it's going to be times by CIS of, let me see, that would be 6 times pi thirds. Okay, now if you notice, 6 times pi thirds becomes 2 pi. Okay, so this is basically 4 to the 6. If we calculate it, 4 to the 6, it's going to be 4096 CIS of 2 pi. Okay, so that one becomes pretty simple. Well, cosine of 2 pi is 1, and sine I of 2 pi is 0. So that actually turns into, if I were to convert this back to rectangular, that would be 4096 plus 0i, which actually is just 4096. Okay, and that's the beautiful thing about it, is just working with it. You can simplify. Now this would be obviously the polar complex version, and this would be the rectangular complex version, which in matter of fact turns out to just be a wholly real number. Okay, now let's start talking about the distinct pth roots of a complex number. Alright, so we're going to find the 3 cube roots of -2 minus 2i. Okay. Alright, and so this is actually just by using the formula. So we got, what we're going to do first is we're going to find r, which is r is going to be the square root of negative 2 squared, which is 4, plus 4, which is just going to be equal to 2 square root 2. Okay. Alright, so that one's pretty simple. And then theta is going to be equal to the arctan of negative 2 divided by negative 2. Okay, since a is negative, we're going to be adding pi to it. Or you could add, oops, you can actually add something. You can add 180 to it, but you do probably want to use pi for this case. Okay, so it's going to be 5 pi fourths. Okay, so technically this all becomes 2 root 2 times CIS of 5 pi fourths. Now we're going to add 2 pi k. Alright. So this is going to be the setup for it. Now what we're going to be doing is we're going to actually be raising this whole thing to the 1/3 power. Okay? Alright, and we're going to go back and use the formula that we just talked about. Okay, so the distinct pth roots of a complex number are going to be, when you raise it to the 1/3 power, okay, is you're going to raise the modulus to the 1 over p power, and then you're going to do CIS of theta plus 2 pi over n divided by 2, or in this case we're going to have p. So let me actually change that real fast. That should be a p. Okay, so that's my bad on using the 2 on there. Okay? Alright. So if we equal it out, this should just be root 2. Okay, CIS of 5 pi fourths plus, no, not theta, 2 pi k. Okay, and we are going to divide that by 3 in this case. Okay. Alright, and so what we're going to do is we're going to let n equal 0, 1, and 2 successively. Okay, so you plug it in and here's what it's going to look like. Okay, so everything gets worked out like this. Now these right here, I accidentally wrote them down. These should be all turning into 12s because we're dividing by 3. So this should be 12 and this one should be 12. Okay, now those are not regular numbers, so you can't just distribute and just have nice clean old things. So here's the actual radicals. Now here's the actual approximate 3 roots that you would actually have. And this is the cool thing about polar works with this, is that if you're trying to find the roots of a complex number, because if you remember, a complex number can actually be an iteration of a function from before. So if you're trying to find out what the iterations were before, you can actually find it out this way, and this is what we actually get. Okay, and you can obviously check the roots by multiplication, so that's the really cool thing about it. You do need the setups like this, and in this case I accidentally said n when it should be k. Okay, and so what you're going to do is just use that to find the 3 roots that you need. Okay? Alright, that's it for working with complex roots and De Moivre's theorem. I'll talk to you later. Bye.